One of the key transformations to learn about with functions is understanding how reflections affect the shape of the graph. So let's start by looking at reflections in the y-axis. These occur basically when you replace x with negative x. So if you've got a function of x and then you want to know what function of negative x looks like, it basically gives you a reflection in the y-axis. Now, why does this happen? Well, let's look at an example to understand it. Here we've got the graph y equals 2 to the power of x. So what we're saying is that if we replace that with y equals 2 to the power of minus x, and we want to know what that looks like, then as long as we know the shape of this graph, we can really quickly and easily graph this one. Now, reflecting in the y-axis means that it's like we've got a mirror here and we're flopping everything over to the other side. So this shape up here is going to come up here instead. And this part that comes down here is going to come down this side instead. And so we'll get the exact opposite reflection. And this will be the graph y equals 2 to the power of minus x. Now, to understand what happens here, let's just consider any given y value on this graph on either side. If we take a y value like, say, here, and think what does that equate to on the y-axis, then whatever x value caused that in the original function, it's now the negative value of x over here that's going to cause the exact same spot. So if this distance here was, say, x, to create this point xy, then we've got the same y value being created now by negative x, which is over here. And that distance from here to here is still x. That's x, and this is y. So it kind of makes sense that whatever y value you used to get from doing a certain thing, raising 2 to the power of something, you now get that same y value from raising 2 to the power of negative x. And that explains why you still get the same y values, but you get them on the other side. Let's look at reflections in the x-axis now. To create these, we're basically replacing y with negative y. So if I take this original function here, y equals 2 to the power of x, what we're saying is that we're going to replace y with negative y. Now, to understand why this is going to flip our graph down like this, y equals minus 2 to the power of x. Notice how I've labelled this here. I haven't actually called it minus y, have I? Now, I could do that. It's exactly the same as this one. But there's a natural naming convention with functions that if we can, we sort of try to write y equals for a graph like this. That's the normal way to write it. So you can see here that the reason this replacing y with minus y flips our graph down here is that we still have the exact same x values that we used to have. So in the original graph, if we looked at some value of x, say here, and said what y value does that equate to, well, now that same x value is in play, but it's now equating to a y value that's equal in size, whatever that was, let's call it y, we now have it equal to minus y. So you can see how for any x value, what they used to get when we put something into the function, we now just get the negative version of it. Now, we could write it like this. This is the easiest way to actually make the transformation, because if you've got something in a completely different form, it's not y equals, it might be a general form, say a straight line or something like that. You can just replace y with minus y. You can then rearrange the equation so that it's in a different form, and it will still have that same shape. Now, when you rotate something 180 degrees about the origin, and graphs that are odd functions have this quality that they are basically, each arm of the function is a rotation around the origin, you get a combination of both of the above reflections, and it doesn't make any difference which order you do them in. So if we were to take a graph like y equals 2 to the power of x and replace, let's have a look at the algebra, replace the x with negative x, but also replace the y with negative y, and we've already seen that you can write the negative there, or you can multiply both sides by negative 1, and the negative will come over here. If I want to graph that, I have to think, well, I've got to either flip it down this way and make that graph, and then flip that one over. It's going to look like this, isn't it? And it will look like that no matter whether I flipped it down first and then across, or if I flipped it across first and then down, this is actually a flipping down of that one, isn't it? So it makes no difference. That's why we say order doesn't matter. But it's a combination of both of those reflections. And we also call this reflecting about the origin. But it's basically exactly the same as if we took every single point on the original curve and we attached that point to, let's say, a bit of string that was also attached to the origin. We could swing it around 180 and that point would end up down here. And this point would end up down here, and this point would end up down here, and so on and so on. So it's almost like every single point on the original curve has been swung around 180, like a big windmill. So when we take a graph we know well, like y equals x squared, we can now understand why y equals negative x squared is a reflection down here in the x-axis. You might think, well, what happens if you reflect it the other way? It's not actually going to change, isn't it? And and that's because y equals minus x all squared. Once we're squaring negative, we get the exact same thing. So making a reflection around the y-axis will do nothing to this graph, but a reflection around the x-axis, which we could write as replacing y with negative y, once we multiply both sides by negative 1, we can also write it like this, and it's negative of the whole x squared, isn't it? And that will flip it down there.